All right, so welcome back everybody for today's session of the Cardiff Analysis Seminar. So today we're delighted to have Rupert from LMU Munich, and he will talk about eigenvalue bounds for Schrodinger operators with complex potentials. So thank you very much for accepting our invitation, and over to you.
Okay, well, thanks a lot for the invitation. It's a pleasure to be here and to see familiar faces. I'm gonna speak about, as you said, about eigenvalue bounds for Schrodinger operators with complex potentials. So this has been an area where there has been quite some activity in the past 10, 15 years. And in particular, last month, we've seen the solution of some of the conjecture due to Sabine Böckli and Jean-Claude Cunin. And I thought I'd take this opportunity and review some of this work that has been done, advertise their result, and also point out a few other open problems that I hope will still inspire some people and some work in this area. So let me describe the setting in which we are going to work. We look at Schrodinger operators minus Laplacian plus V, and we consider them as operator in an L2 space. And about the potential, we will always be assuming that at least in some sense, it's smaller than infinity. So in some sense, you can think of this as really a perturbation of the Laplacian. Okay, and so the other thing that we want to do is we want to quantify all our assumptions on the potential V only through LP bounds. Okay, so no pointwise bounds, no derivative bounds or whatsoever. Just V should be in LQ. And so on the one hand, I told you already, I want to have Q less than infinity because I want to have the potential smaller than infinity. On the other hand, I want to have Q sufficiently large, just that I can define the operator so that I don't have too bad local singularities. And there are specific conditions on Q, and those will appear later when we talk about it. But for now, let me just say that if Q is sufficiently large, then there's a theory of M sectorial operators. That's roughly the same thing as quadratic form technique for a self-adjoint operator. And then you can define this operator as an M sectorial operator, and that's fine. And now at this point, one usually cites the book of Edmonds and Evans, which has 7 different definitions of the essential spectrum. Now, in this particular situation, all these 7 definitions coincide. And so the outcome is that outside of the positive half line, 0 to infinity, the spectrum of this operator consists only of eigenvalues, and all these eigenvalues have finite algebraic multiplicities. And if the eigenvalues do accumulate, and they can only do so on the positive half line. Okay? All right. And the subject of this talk is what can we say about these eigenvalues that sit out there in the complex plane outside of the real axis. And more precisely, we will divide this study into 3 parts. Namely, first of all, we say, what can we say about a single eigenvalue? Where can eigenvalues live? Given, as I said, only the size of the potential in LQ. Secondly, I want to say something about more than one eigenvalues, ideally about all the eigenvalues, right? What can we say about their sum or the sum of their powers? And the last subject, which is probably the one that is least developed, is what can we say about the number of these eigenvalues? And as I was already saying at the beginning, there has been great progress concerning this first item, which I think by now can be really considered as solved by Böckli and Cunin. But concerning these other 2 points, there are many unresolved questions. And I should also say right now that what I'm doing is by no means any theory of non-self-adjoint operators. We really look at one very particular, very special case where we can say a lot. And we should always keep in mind, so our V's are smaller than infinity, the perturbations of the Laplacian, and therefore the results that we hope to establish should be relatively close to the real case. Other people, for instance, the group around Johannes Sjöstrand, have studied such operators for much larger V. right, which either grow to infinity or which are on compact manifolds and stuff. And then the non-self-adjointness is a much stronger perturbations, and they can create much, I mean, from a self-adjoint point of view, much less regular situations. However, as you will see, the situation, even in this restricted setup that I'm considering, will be quite surprising, at least for me. All right, let's start at the beginning. Let's talk about individual eigenvalues, okay? And again, let's just, in order to see what we expect, let's recall what we know for real potentials. And so there's a paper from 1961 by Keller where he asks sort of an isoperimetric question, and he asks, how small can I make the lowest eigenvalue of a self-adjoint Schrodinger operators when I'm fixing the LQ norm of the potential? Okay, and he discussed this problem and talked about it. It's not really rigorous according to modern standards, but actually unaware of this paper, Lieb and Thiering in 1976 arrived at the same problem, and they really solved it mathematically. And essentially everything about this problem that you want to know is known. And if I just write the very basic information down, is this bound, okay? So the eigenvalue is always the eigenvalue for me. And it's convenient to denote the power of the potential as gamma plus d over 2. And then you put the gamma there. Okay, and then more or less by scaling, if this problem, if there's an optimal potential, if this problem makes sense, then you have such an inequality. Okay, and so the only thing that you can think about is do you have any restrictions on gamma? And these are only the natural conditions, namely in one dimension, right? You want to have at least an L1 norm. The power of the potential should be at least 1. So we always will assume that gamma is greater or equal than a half in dimension 1. It can be any number greater than 0 in dimensions 2 and higher. And as I said, the question that we ask ourselves is how much of this does survive for complex potentials? And actually, I guess the first group of people who asked this question was in 2001, Brian Davis and collaborators, and they actually could prove that in the one-dimensional context, it is true that the square root of the absolute value of any complex eigenvalues of this Schrodinger operator is bounded by 1/2 times the integral of the absolute value of v. Okay, so that's sort of the prototypical bound. We want to prove exactly bounds of this form. And not only, I mean, is this result by them remarkable because it asked the question and answered it in one dimension, it's also remarkable because this constant that you see appearing here, this 1/2, this is actually the optimal constant. And even more, this constant 1/2 is exactly the constant that appears in the real valued case. It's actually the same constant that appears in Keller's 1961 paper. Okay, and so if you're now an optimist, then you might think, well, perhaps there's something at work, some sort of maximum principle or something that always gives you, whenever you have the constant in the real case, then you also get the constant in the complex case. And then we would be very happy and we would have the complete picture. Unfortunately, that is not the case. Okay. And so the first baby, very toy example is here in a German paper with Laptev and Schrodinger, where we looked at essentially the same operator as Davis and company, except that we look at it on the half line. We put a Dirichlet condition, and surprise, what happens is that you have to increase the constant by a factor 2. All right. So, I mean, that still you might think at first sight, well, you still have the inequality. Perhaps you don't care whether it's the constant is 1/2 or 2, 1/2 or 1. You still have an inequality. But already, I mean, the point I'm trying to make, it's really an indication that something happens in the complex case. And so right, that's what I wrote down here. We see that we cannot expect to have the same constants in the real case as in the real case. And that's an indication of a phenomenon which we will see in a little bit, namely that we actually will not even have the same range of exponents in the inequalities. Okay, and then you see also here, I've plotted this picture. What you see is, look at, I mean, right, I was talking about potentials in L1. It's not such a big step if I take delta functions, delta potentials, multiplied by a complex coupling constant. And then I can, because I'm on the half line, it matters where I put my delta. And if I optimize, so for given C, I can optimize over the position B. And then I see that the eigenvalue traces out this dark black curve. Okay, so you see in the middle, the dashed line, those are the eigenvalues on the whole line. Okay, that's the circle here of radius 1. It's normalized to be 1. When I now add my Dirichlet boundary condition, well, and if I want to have a bound which holds for all eigenvalues, then I have to increase this 1 up to 2. Okay, and this is how you get twice, why you need to have twice the constant. However, there's another lesson that we learn from looking at this picture, namely, really where things change significantly from the self-adjoint case, this is close to the positive real axis. See, when I'm over there, eigenvalues say in the left half plane, I don't see much change between the real case and the complex case. Okay, so let's keep this in mind. Eigenvalues close to the positive real axis are the troublemakers. And we will see soon how much trouble they actually can make. All right, so now here's the slide that gives essentially a complete answer about this Keller problem in the non-self-adjoint case. Everything started with a conjecture by Ari Laptev and Oleg Safronov in 2009, and they said that such a bound, right? This is the same bound that we've seen in this on the previous slide that was conjectured by Keller. Laptev and Safronov conjectured that such a bound holds in all dimensions greater or equal than 2, and for gamma up to d over 2. All right. So Laptev and Safronov were the first one who somehow apparently came to the belief that this bound may not hold for all gamma. It's not completely clear to me how they came to that belief. And in particular, why they came to, I mean, that it's a finite number, and even less so why they came to that number. It's a bit cryptic what they write. They seem to have been thinking about the Wigner von Neumann potential, and that actually gives some intuition, but as you will see in a second, this is not the whole story. Okay, so a couple of years later, I was able to prove their conjecture in a restricted range. Namely, instead of the d over 2 that they believed, I could prove the inequality up to gamma equal to a half. All right. There's perhaps a little technical thing that actually the bound holds even if it should be an embedded eigenvalue. That was, I mean, that's a bonus of the inequality. They didn't state such a strong conjecture. Anyway, then 10 years passed, and then now last month was this paper that I alluded to already by Berkeley and Cunin, who actually showed that this restriction gamma equal to 1/2 is actually optimal. In other words, this conjecture of Laptev-Safronov fails for gamma greater than 1/2 and smaller than d over 2. Okay, so in other words, what they constructed is a sequence of potentials for which this normalized, this is a dimensionless quantity. So either you fix the eigenvalue to be 1, and then you make the L infinity norm, the LP norm of V go to 0, or you fix the norm of the potential and you make the eigenvalue go to infinity. Anyway, so they showed that no such inequality can hold. And this is really a very nice result. And many people have tried to prove this, and they were successful. And just to show you, I mean, how strong this conjecture is, or perhaps the non-conjecture, the disproof of the conjecture. Once you have this theorem, it's actually a simple exercise to show that for any gamma greater than 1/2, there's a potential. This potential belongs to this L gamma plus d over 2 space. It can also be taken bounded such that every point on the positive half line is an accumulation point of eigenvalues of the Schrodinger operator. Okay, so the eigenvalues can accumulate at every positive number. At the same time, your potential doesn't need to be bad, right? I mean, it's a bounded potential. It's just not super fast decaying, but not very slow either. Okay. As I said, I mean, this statement here is not so complicated consequence of this theorem. Just if you have one crazy eigenvalue, then you can place lots of copies of V very, very far apart, and you get lots of crazy eigenvalues. Anyway, so that settles this question of Laptev and Safronov. And I want to step back a little bit and tell you a little bit about the proof of this theorem up there, because I mean, it's not only the result, but it's also the idea that was behind the proof, which showed a new phenomenon that arises in the complex case, which is not present in the real case, and which explains why gamma equal to 1/2 is the limiting exponent, and why Berkeley and Kühner were able to construct this counterexample. Okay, so this is a bit technical, this slide, or making big steps. If you feel uncomfortable with this slide, you can just take a short break and continue on the next slide, okay? So, but for those who want to stay, it's perhaps not surprising that when you talk about eigenvalues, then the Biermann-Schwinger operator comes in. Okay, so the Biermann-Schwinger operator, that's a square root of the potential, a resolvent, and a square root of the potential. And if you only know that your potential belongs to some LP space, well, then multiplication by that potential, or the square root of that potential, maps from a certain LP space to another LP space. Okay, good. So having that in mind, we look at the norm of the resolvent, not as an operator from L2 to L2, because then we know everything, but from some LP space to its dual. Okay. And once we have such a norm, as I told you, then we get a bound on the Biermann-Schwinger operator as an operator on L2, just by Hölder's inequality, right? So this is our purpose. Our purpose is to understand this resolvent bound. And this is now very much in the spirit of the limiting absorption principle. See, Koenig-Rees-Sorg proved a bound on this resolvent, which does not get bad if Z approaches the positive real axis. It's uniform in the argument. Of course, just by scaling, you know that it depends on the absolute value of Z where you play it, right? Everything scales. But on each ring, it's uniform in the argument. All right. And so they proved this for a certain range of P's. And so this number is not very surprising. This just comes from the ordinary Sobolev embedding. The new thing that Koenig-Rees-Sorg noticed is that this upper bound on P. And this upper bound on P comes from the so-called Stein-Thomas inequality in harmonic analysis. Let me jump to that inequality. And well, the relation is, roughly speaking, see the resolvent, right? When you approach the positive spectrum, then sort of this resolvent sort of develops a delta function. at the point you're approaching. And this delta function, that operator, that's essentially the operator that's behind the Stein-Thomas inequality, even if that's not so clear. Anyway, so let's talk about the Stein-Thomas inequality for a moment. The setting is now the following. We take a function f, which lives in L2 on the sphere. I multiply, and I'm taking roughly the Fourier transform of this function. It's not the real Fourier transform, right? Because the function only lives on the sphere. But just imagine the function. Think of the function as a distribution. Think of it living on the sphere. And you take the Fourier transform, and the theorem is that this function is integrable in Rd to some power. And if you look at this power here is exactly the dual of this power. So this explains why the two inequalities are essentially the same. Okay, and it's exactly this power that we have to talk about. Namely, what I want to tell you now is, in order for this to see that the Stein-Thomas inequality cannot hold with a better power than the power there is written here, one looks at the following. It's a so-called NUP example. Okay, so you pick your function f here to be the characteristic function of a tiny little cap around the North Pole. And let's call the size of this cap, let's call it epsilon. Okay, and now we compute this Fourier transform. So, right, we have this tiny little cap around the North Pole. And it has in the downward directions, if I think in 3 dimensions, its projection in the xy plane has size epsilon. But now, because of the curvature of the sphere in the z direction, it has size epsilon squared, right? So just a naive heuristic with uncertainty principle tells you that the Fourier transform, what you get out of this integral, roughly speaking, lives where the variables corresponding to the xy variables live where they are 1 over epsilon, and the remaining variable is 1 over epsilon squared. Okay, that's just because the Fourier transform somehow inverses the length scale. All right, so just keep this in mind. This is kind of how you show that this inequality is saturated, how you show that this is the best power. Correspondingly, this is how you show that this is the best power. And now when you do this Biermann-Schwinger argument, you see that this power is exactly the power that corresponds to gamma equal to 1/2. So what I'm trying to tell you is what's behind this bound, this theorem down there, is this restriction phenomenon, okay? Or the saturation for these caps. And so you go somewhat roughly through this analysis, and that was done first by Ionesco and Jerrison in 2009. You can use this to construct, now in the completely real realm, okay, you can construct a real potential which has an embedded eigenvalue and which is essentially supported in this set. So the point I'm trying to make is this is a completely different construction from the Wigner von Neumann construction. Okay, Wigner von Neumann construct a radial potential with an embedded eigenvalue. Here, what they do is a potential that's very fast decaying in d-1 direction and elongated in the remaining direction, or slower decaying in the remaining direction. Okay, and as I said, it was known since 2003 that you can have such embedded eigenvalues. And you can also see that these eigenvalues would contradict such a bound. The only point was that those eigenvalues are real eigenvalues, whereas Laptev and Safronov actually wanted a bound for complex eigenvalues. And so in a nutshell, what Berkeley and Quenin did is they could do such a construction where they push the eigenvalue off into the complex. Now, that's by no means trivial. I mean, that's what people have been trying for quite some time because, well, because it's difficult. I mean, let me put it differently. Even the Berkeley-Kuhnert result, they don't write down an explicit potential. They do a rather complicated and quite ingenious construction to say that there is something which has certain properties. But it's not a constructive proof per se. Anyway, this was the technical slide here. Perhaps the takeaway message is that radial potentials are not the enemies, as you might have thought, but really rather these needle-like potentials, right, which are extended in one direction much longer than in the other directions. And so if you have this in the back of your mind, you can come up with a couple of other inequalities that you can prove. I don't want to spend too much time on them. It's always, there's a theorem, and then there's a second theorem telling you that this is optimal. Okay, so the first theorem is, yes, you can go beyond the 1/2 threshold, actually up to the d/2 threshold that Laptev and Safronov conjectured, if you have a radial potential. Or put differently, you can take an arbitrary potential, but then you should not take the LQ norm, but rather what you should do is for each fixed radius, you should optimize over the sphere. Okay, so that sort of kills these needle-like structures and pushes the inequality up to that exponent. And then Berkeley in 2017 showed that this restriction, now the d/2 restriction, is optimal. And so she actually constructed a sequence actually of radial potentials that, I mean, show that this inequality cannot hold if gamma is greater than d/2. And then there was another result. So, I mean, so one way to go beyond 1/2 was to add a radiality assumption. Now, the second way you can do is you look at bounds of a different type. Okay. See, what you want to have is the eigenvalue to the power gamma. Instead, you can split the power gamma as a half and a gamma minus a half. Now, the quantity that I take to the power gamma minus a half, that's a quantity that's less than the absolute value of E itself. It's a quantity that does coincide with the absolute value of E, however, in the left half plane. That's where we don't expect any troubles. Okay. However, it goes to 0 as I'm approaching the positive axis. Okay. So this thing makes the inequality weaker. And the theorem is that if you write the left side in the inequality in that way, then you actually do have an inequality for any gamma, even gamma greater than half. Okay, so if you like to think about the eigenvalues, I mean, it's not exactly this picture because it doesn't close, but really goes on all the way to infinity. So there's a power-like decay, right? So the eigenvalues are in kind of in a disk around the origin, union with a power law decaying shape that extends all the way out to infinity. That's the information on the position of eigenvalues that this bound gives you. And now you could, of course, ask, I mean, here I decided to write the powers as 1/2 plus gamma minus a half. But of course, you could ask me, can I increase this power? Can I make this power greater than a half and correspondingly make this power less than gamma minus a half, right? Because then the inequality would be stronger because I would take a smaller power of this small factor. And what Berkeley and Kuhnert proved in the same paper months ago is no, you can't. Okay, so they also showed that this gamma to the minus 1/2 is optimal. Okay, this is a little bit complicated to read here. So you look at, this is the quantity that's written here, and you look only at eigenvalues which are close to the, I mean, in a cone around the positive axis. And no matter how small you make this cone, you can make this, keep this positive. Okay, so just in words, it means that you cannot change this power and you cannot improve this power. Anyway, so these were two ways to go beyond the Laptev-Safronov, or to go beyond the threshold gamma equal to 1/2 in this problem for single eigenvalues. What I want to do now is I want to talk about several eigenvalues. Okay. And again, I look at the case of real potentials to get an idea of what one could expect. And so this theorem, which goes back to Lieb and Thiering in 1976, and then Timo Weidel provided an endpoint case in 1996. This theorem states that I have an inequality very much like Keller's inequality I had at the beginning, but now I take all the eigenvalues on the left. Let me go back. See what I see here, even there, right? This is a single eigenvalue to the power gamma, is controlled by this quantity. Lieb-Thiering proved that if you possibly change that constant, then you can actually sum over all the eigenvalues E on the left side. All right, and that holds under the very same assumptions on gamma as for the single eigenvalue. Once again, the question that I would like to ask is how much of this Lieb-Thiering theorem survives for complex potentials? And so we looked at this in 2006 and showed that at least for eigenvalues which are away from the positive axis, meaning I'm looking at a cone around the positive axis, right? And I'm looking at eigenvalues which lie outside of that cone. For those eigenvalues, everything is fine. For those eigenvalues, the inequality looks just like the inequality in the real case. Well, of course, there's a price to pay, namely that the constant depends now on the opening angle of that cone. And of course, if that cone shrinks to the axis, then the constant diverges. Okay, so keeping this in mind, we should always remember that what we really are interested are these eigenvalues close to the real axis. In order to motivate what's going to come, let me recall an observation that Demuth, Hansmann, and Catriel made in 2009. They looked at this bound here. This is a bound which depends on kappa. And I can just average this bound with respect to kappa. Okay. And then what I get a weaker bound. And this has the form that I have the eigenvalues to the power gamma. And then I have such a factor, again, distance to the real axis divided by absolute value. Okay, so I have here a factor which is less than 1, and I'm taking this again to some power. And for such quantities, I have now an inequality by the power of the potential. Okay, so Lieb-Thiering inequalities where I make this term smaller as the eigenvalues approach the real axis. Now here's the currently best information that we have about this problem. I actually do make it a little bit more general. I'm taking the eigenvalues to the power alpha. I'm taking this factor that we've already talked about, right? Taking that to the power beta. And then what I'm allowing is that I'm taking an outside power gamma over alpha, such that the overall homogeneity of this term is, again, eigenvalue to the power gamma. Right? So by scaling, everything has to be scale invariant. If I have a bound, then this should be in the terms of the, should be in terms of the integral of v to the power gamma plus d over 2. All right. Now the question is, for which values does this hold? And well, here are 6 different cases for which we can prove the inequality. All right. I don't want you to read this. I know this is complicated. Let me just point out one, which is perhaps the easiest one to read. Namely, if I'm in one dimension, I'm at gamma equal to 1/2. I'm taking now the sum of the distances of the eigenvalues to the real axis. And I'm raising this to the power 1/2. Then this is controlled by the integral of the potential. Okay, see, that's a little bit similar to this Davis bound that we had before. It's also a little bit similar to this Liptiering bound, but you see, importantly, the power is outside. The 1/2 power is outside the sum and not inside the sum, which is worse, right? I mean, the inequality would be better if we had the 1/2 power inside. Anyway, let me comment. So here are the bounds again, written in this typical form. Okay, now my first observation is that if I look at, remember, there's this example, this crazy example by Berkeley and Quenin, where these eigenvalues accumulate. Now you might ask yourself, how fast do they accumulate? So this would mean we're looking at these powers beta. The powers beta, right? We look at eigenvalues, just the one sequence of eigenvalues that accumulates at a value. There you can essentially ignore all these values. And what's relevant is the power beta. Beta controls the rate of accumulation. And what our result gives is that if gamma is less than 1/2, that's the same 1/2 that we've been talking about before, right? If gamma is less or equal than 1/2, then you can choose the power beta to be equal to 1. So this accumulation, the eigenvalues are summable. This accumulating sequence is summable. So they accumulate reasonably fast, is how I read this. Okay. Now, that's one remark. And that's, as I also said, I mean, this is really the best there is at the moment. I don't think anybody has an idea to how to prove or discuss whether eigenvalues can accumulate faster. All right. Now, the next observation I'm trying to make is about this power that we've seen here out there, which does not happen in the real case. And, you know, it's a very important feature actually of Liptiering inequality that they actually bound a sum by integral. Because that's a very much, if you think about it, this is a very local way of thinking. It really means that if V has two bumps, one bump here and one bump there, then the eigenvalues are sort of bounded by the sum of the two bumps. So you can almost think that the eigenvalues are the sum of the eigenvalues. It's not quite right, of course, but you know, it is true in some asymptotic regimes, and these are exactly the regimes where Liptiering is effective. And the point here is that in this non-self-adjoint case, we lose this locality. And then you might, of course, ask, I mean, is this just because we use a bad proof or a bad method? Or is there really a violation of locality in these bounds? And I think, I don't know the answer to this, but I have the impression that there is really some problem with locality. Okay, then let me give two items here why I believe that, but that's, I mean, an open question. So on the one hand, there was a conjecture in a couple of years ago where they specified a bound with alpha equal to gamma. So that would be a local bound. And now another result of Sabine Berkeley is that this is wrong, at least in one dimension. So Sabine Berkeley and Stampach were able to disprove or show that this side really can grow faster than this side. And so there is something in this sum that needs to be, that grows fast and needs to be made smaller by such a power. And more clearly, even Jean-Claude proved that if you look at all such inequalities, right, they're parameterized by parameter beta, then this cannot hold when beta is less than 1. right? That's what I told you in this inequality down here. I would be happy if the 1/2 would be down there, because then that would be the real inequality for real potentials. Now, Jean-Claude showed that this is not possible, that this bound here is actually best possible. And that, I hope, gives some indication that perhaps other parts of this theorem might be best possible, or at least not bad either. But I mean, this is all, you see, these are all very, very new results. It's a very active area of research. Let me say, let's see, I'm looking at the time here. Let me say very briefly something about how one proves these things. Essentially, there are two different proof techniques. The first one is an operator theoretic approach, using these words in lack of a better word. So this is started by Cato. He looked at some general operators and just compared eigenvalues of two operators. And then Huntsman, about 10 years ago, was able to improve actually substantially this result of Cato. And you can further play with this result of Huntsman. So this is naturally stated as a result about bounded operators. So you need to play around with to fit your Schrodinger operators in there, go to resolvents or powers thereof, and play with some bounds. Anyway, this is one method that you can do. And the other method is using a harmonic complex analysis, namely you build a function whose zeros are exactly the eigenvalues of the operator. That's usually what a determinant does. And then you have two goals. On the one hand, you need to understand now bounds on that function you've constructed. And that's if you remember, how did we do this for the single eigenvalues? Well, we used these uniform Sobolev inequalities. Those give you boundedness of an operator. If you upgrade these boundedness conditions to compactness conditions, and more than that, quantitative compactness conditions, meaning trace ideal properties, then you get bounds on several eigenvalues. That's at least a very natural way of thinking about this. Well, so you produced some bounds on this analytic function, this determinant that you've constructed. And then it's a problem in complex analysis, and actually a quite interesting one and non-trivial one, to get from bounds on this analytic function information on its zeros. Okay, so the basic thing that you might have in mind from complex analysis is this Jensen's formula, right? Jensen's formula tells you how the zeros are related to an integral of the analytic function on the boundary. And you can roughly think of these theorems as far-reaching generalization of this Jensen's inequality, where things are quite complicated because you have different singularities. Okay. Anyway, but you see, I mean, this, if we go via analyticity, then getting a power beta equal to 1 is the best we can. This is related to this Blaschka condition on the zeros of analytic functions. And if you use the operator theoretic approach, then you get even worse things because you use a worse input. As far as I know, these two ways of approaching this problem are rather disjoint. And I've never been able to combine them and somehow combine their strengths. And anyway, but I would be happy if somebody could do this. Let me now, at the end of the talk, come to the final subject, the third subject I was mentioning, namely, what about the number of eigenvalues? Okay, and this is perhaps the most surprising difference to the real case. Namely, there's a very old case. I mean, we're again looking for inspiration at the real case. Okay, and then we know that what makes the transition between finitely many negative eigenvalues and infinitely many negative eigenvalues happens at a 1/x² decay. Okay, And I've written down here the simplest version of this. So if your potential decays faster than inverse quadratic, then you only have finitely many negative eigenvalues. If it really decays slower than inverse quadratic, then you have infinitely many. And again, you ask yourself, I mean, how much of this survives for complex potentials? And there's a resounding nothing as an answer given by Pavlov many, many years ago. And let me state some of Pavlov's results. And they show you really how different the complex world can be from the self-adjoint world. So what Pavlov says is that if your potential decays like the exponential of a negative square root, then you only have finitely many eigenvalues. Okay, so that's a much, much faster decay. It's almost exponential decay. Not quite, because you have the square root sitting up there. On the other hand, if you don't have a square root sitting up there, but some number which is less than a half, then actually you can have infinitely many eigenvalues. Okay, so Pavlov tells you that the transition between finitely many eigenvalues and infinitely many eigenvalues happens at an e to the minus square root of x scale. Okay, and he did this. So these are beautiful works. To Pavlov, they use a lot of mathematical ingredients, and I think the most significant ones are theorems from complex analysis. I mean, really, really non-trivial theorems from complex analysis. But what one also has to say is that these theorems that he uses are not quantitative. So meaning he says that if you have this bound, then you have only infinitely many eigenvalues. And he essentially argues by contradiction. If you had infinitely many, then you had something that would contradict some big theorem in complex analysis. Okay. And so the question that comes up naturally is, can we do something quantitative here? Say, given a potential, so now I'm leaving my LQ world, given a potential that satisfies a bound like exponential of minus b times x to the alpha, a constant d, can I bound the number of its eigenvalues, of its eigenvalues in terms of the parameters alpha, d, and beta? Now, if, and I'm always assuming that alpha is greater or equal than a half, because if alpha is less than a half, then there's no way, right? Okay, now if alpha is equal to 1, this is an easy problem, right? Because then your potential decays exponentially, so your solvent can be continued across the spectrum, analytically continued, and then you can play, for instance, with the ordinary Jensen inequality. And you can do this in a little bit more complicated way. Anyway, but the important question is, what happens if you have such a decay where alpha is strictly less than 1? And I don't know the answer. I can tell you one theorem that we proved. And again, you see this is the form of the theorem, if you just look down there, is not particularly appealing. It's the best that we know at the moment. So let me walk you through this theorem. So we do not look at Schrodinger operators, but instead we look at Jacobi matrices, which is, I mean, you could look at discrete Schrodinger operators, right? I mean, you could just take all the A's and all the C's to be equal to a half, and the B's are then your potential. Right, and so we assume that these coefficients, here they are, satisfy such a bound. Okay, that's exactly the bound we had on the previous slide. It's the exponential with an n to the alpha, and then there are my two constants b and d. And then, so let's just look at the case where we have e to the minus square root of n. Then at least the bound says that these eigenvalues do not grow, the number of these eigenvalues does not grow faster than roughly the square root of d. E to the square root of d. Okay, right. So I'm looking at imagine B is a constant. And you can think of this A parameter that appears here as essentially as D, as the coupling constant. B is the coupling constant of the potential. And then, so B we said was a constant. And then you have here the square root of A. That's what we said, that was the square root of D. And if alpha is greater than a half, well, then what you get are bounds that are polynomial in A, meaning in this coupling constant D, where the power of the polynomial depends on how close alpha is to a half. Okay, so how do we prove this theorem? Again, using this identification of eigenvalues as zeros of analytic functions. And what we do is we prove a theorem about zeros of analytic functions. Okay, this is a quantitative version of this theorem that Pavlov uses. And we also show that within the realm of complex analysis, this is an optimal theorem. Okay, what we do not know, however, is whether this bound is sharp also for Jacobi matrices. Okay, so I don't know whether you can saturate these bounds. If you say let B be a parameter that converges to something, or that D is a parameter. Okay, I don't know this. And more general, what's behind this is, see all these results that we have so far, or quite a number of these results, use the connection between zeros of analytic functions and eigenvalues. And so if we would know that these determinants that appear there are better behaved than arbitrarily analytic functions, then, I mean, we would try to use this. But so far we don't know, right? So far we treat these determinants just as ordinary as arbitrary analytic functions. So the question is sort of, which extra property do these determinants have some extra properties that we could use? Or is it almost the opposite true, that almost to every analytic function in the disk, there corresponds an operator? I mean, of course, there's symmetry restriction and normalization restrictions. But I mean, how do these two classes of functions compare to each other? And even put differently, right? The question, what I told you here, I mean, we get a bound here that says that in the worst of all cases, the bound grows like exponential of the square root of the coupling constant. Can it happen that we have so many eigenvalues? Or an even more basic question, I mean, can one construct operators with complex potentials that have really a lot more eigenvalues than their real counterparts? Roughly speaking, what Berkeley, Stampach, and Quenin did is they showed that something like this can be done in 1D. And roughly what they had is they had logarithmically more eigenvalues with respect to a natural semi-classical parameter. I mean, that's not much more. I mean, the question is, can you construct much, much more eigenvalues, right? I mean, they had the examples in where they constructed the counterexample, you had over here, you had polynomially many eigenvalues, and they had a log more than those. Now the bound here would say it might be, I mean, it says that it cannot be more than an exponential number of eigenvalues. So where is the truth there? And can one construct such eigenvalues with more potential? I get such potential with more eigenvalues. And let me finish with my last comment, which is perhaps a little bit more like a dream. Remember I told you about these examples with gamma equal to 1/2 and these elongated needles, right, which saturated the bound at gamma 1/2 and were used to construct a counterexample beyond 1/2. Now, many of these needles, they were used by Pfefferman to disprove the so-called disk multiplier conjecture. And this was really a big step in harmonic analysis in the 70s. And this started all this field of Kakeya problems, where you have exactly these needles, right? And you ask about how big a space do they have. And somehow the question that I would like to put out there is, can one somehow use these constructions of many needles to produce many eigenvalues? And I don't know the answer. I would be happy if one of you does. And for now, I would like to thank you for your attention. Thank you.
Thank you very much.
Thank you.
So, do you have any questions for the speaker?
Could I ask a stupid question? What about lower bounds in the non-self-adjoint case? Are there any results that give lower bounds in the number of eigenvalues?
No, I don't know of any. I don't know of any. It's hard to imagine. If you look at single eigenvalues, you might still think that if you, change the coupling constant, the eigenvalues might appear and disappear through the continuum. So I'm not sure how one could phrase really a lower bound there. It's of course something else if you have several eigenvalues. And I guess in some sense, this, if you talk about asymptotic lower bounds, then this is almost this question that I was asking at the end, which I find very interesting and which goes exactly in these directions of this, where you disprove these bounds, right? In order to disprove these bounds, you prove, say that such a sum is actually huge. So you try to create many eigenvalues. And this is where I guess we have even less understanding than to prove upper bounds. So I do think that this is very interesting.
Thanks.
Thank you.
So further questions?
Can I ask something?
Yeah.
Yeah. Hi, Rupert. Very nice talk. Thank you. I remember that you once said that there is this this device of Swarovski where he proved he uses determinants where you don't use the regularized determinant,
Right,
but you
right.
put the power of the
Right.
operator inside the determinant. Do you know whether this technique has been explored, whether you get better results doing this?
No, I don't. This is an idea that also comes up in my head every time, even this morning when I prepared the talk. So, let me say this, for instance, here. I was not always saying which function I exactly construct when the function whose zeros are their eigenvalues. And so here I wrote perturbation determinant. But an ordinary determinant is not good enough, but rather you have two choices because of convergence issues. Either you take the modified perturbation determinant, or you take the ordinary determinant, but of a power of the resolvent. And it was crucial for Swarovski to do the second one. That's what I hear, and not do the first one. And I've never understood why it was really crucial for him. But I think it's something that one should explore, and perhaps one would learn something, yes. But still, I think as soon as you deal with analyticity, I don't think you can ever improve an accumulation beyond a summable. That's simply what Blaschke products give you. So if you want to prove, or if somebody wants to prove a faster decay, he would need to use different devices. Or again, to come back to the previous question, perhaps prove counterexamples. right? I mean, these examples of Berkeley and Berkeley-Kühner, where you have these many accumulation points, they are somehow not really constructive. I mean, they're not non-constructive, but you don't have any control how fast this stuff converges. And studying this, I think, would be very interesting. And I really think we would learn more about these operators.
Okay, thank you.
Thank you.
More questions? Doesn't look like that's the case. So let's thank Rupert again for the very nice talk.
Thank you. Thanks a lot. It was my pleasure.
Thank you very much.